This is Jingyi with V numbers 9, 7, 3, 2, 8, and 7. So this is demonstration for the simple algorithm in the assignment 3. For this one, we can see this like a company working with lots of workers, and we have one worker named I, one worker named count, one worker named comparison, one worker named output. They do different kind of jobs. They keep things in their memory. If we are telling them something, they will remember, like storing memories in the computer. So for this algorithm, basically what we do is what tell I is you have 0, that's counting how many rounds we're around, which pair of the array are we comparing, and for counting we have 0, start with 0 because we didn't count anything yet. We can have more if we find more things that's bigger than bigger in the array 1 than array 2. So when we go into the loop, before the loop we have to tell I, all right, you listen up, is your number, the round number cannot be bigger than bigger or equal to 6, which means we are doing 5 rounds. And inside the loop, first of all, we have to make comparison to the compare person to ask I, okay, which pair are we comparing, which round? So he have 0, look at the notebook, okay, he have 0 on his notebook. We're to compare the first pair, which is 9, 9. The way he do it is use of A1 minus A2, we got 0, which doesn't mean A1 is equal to A2, that's not bigger. So in that case, he will tell the output, okay, we got tell the manager or the owner or the user, nope, we didn't get anything. And if that's done, and he also tell the I number will say, okay, we're finishing with this round, let's plus 1 to myself, and his notebook will have 1. And we do the same loop again, comparison, compare the number, the pair of number on I's notebook. Okay, I have 1, so we compare the position 1 pair. And for computer, the index is from 0 instead of 1, different from humans counting. But other than that, for the second one, we have 9 and 7, and after comparison, you find out 2, and that's bigger than 0, which means 9 is bigger than 7. And he have to tell the output, okay, tell the manager or the user or the operator, okay, we have 1, that's 9, much bigger than 7, and we found it. And also tell the counting person, all right, we have 1, count 1. So he plus 1 on his notebook, and we keep the looping and looping and looping, and in the end we're gonna have compare 0, 3, 7, 2, 1, 8, 3, 7. So we got 1 nope mark, and which is nope, and we got a check mark and 9 bigger than 7, and nope mark for 0, 3, 7, 2 check mark, 0, 9, nope, and 3, 7 is nope. So we got this one is 7 bigger than 2, and these are my outputs. And in the end, we should get counting, as a count number should be 2 because we have 2 check marks. And the comparison count to count twice already. And also in the end, we have to output the count, so which is 2. And in the end, we're gonna have, that means 2 numbers in array 1 is bigger than the corresponding index in array 2. In array 2's number, okay. And this is a demonstration for insertion sort. We have a random bunch of books we haven't sorted yet, so we can sort them from the shortest to the tallest, from the water bottle to the right. How do we do that? With the insertion sort. And basically every time we check the 2 books from index 0 to 1, then let's see is the second one taller than the first one, and we have yes over here, so we keep where they are. And then we do the same thing for the next one, compare it with the previous, all the previous index, so include the first one. And in this case, yes, it's good. It's taller than the second one, which means it have to be taller than the first one. And for the next one, we have a very tall one, for sure. We know, yes, the length of it is bigger than this one and this one and this one. So we don't need to compare, we only compare this pair. And for next one, we have this. Oh, now we have one that's a little bit shorter than the previous one. So we switch there. We insert this one, the shorter one, from the previous position to the next position. Then we do the comparison again. Oh, now it's taller than the previous one, so we keep it where they are, and that means this one is taller than this, this, and this, because this one is taller than this and this. And for our last one, if we compare it with this, obviously we have to switch and insert it to the previous position. And in the computer, every time we have to, when we switch them, like we're gonna do over here, actually is we store this information in another place, and then we put that in the corresponding index, the previous index. Then we remove it, we insert this from another memory, and we gonna do the same thing until we have, oh, this one is taller than this one. That means it's harder than this, this, and this. So to keep in mind, the most important thing is when you're taking out a value, you have to store it somewhere else to make sure you can insert it later on to the right position where it should go. The demonstration for Huffman's code, the third part, the extra part for this assignment. And I'm imagining this with a person have idea for a show, and he have a bunch of characters or actors in his mind that will show up on the stage a few times. For this one, he show up in the stage 19 different times, and there's only 2 times. Some character is just not that popular. You don't need to use them that much. And when he writing the script, he's thinking, all right, I need code them and give them a code because they don't have a name, and they have to be unique to each other. And in that case, we don't need to write some long name for 19 times. And he started using the Huffman code. The Huffman code means binary tree, and you start with a root and you go to each the tree, and you're gonna reach to the end, always the end, find the value or the person or the code you need for your character. And we always start from the farthest. We got 1, 2, 4, 3, 5, 19. Those are how important the character is, and we start from the farthest, which means the least 2 important character, which is 1, 2, and we put them into a group, and it gives their importance increased because in the group there are 3 as a total. And we have the importance of 3 and the importance of 3. Over here, we forming them into a bigger group over here, and that gives us of importance of 6 for this group, containing a small group and character 3. And then we do repeat the same thing. We got 4 and 5, and they are now the least important character. We have to put them into a group, forming a 9. And we have 2 groups, 6, 9, and 1 person 19. That's very important. So we have to forming the 6 and 9 group together as a huge group to have an importance of 15. Then we can finally put the 15 and 19 together to make sure this character get reached from the root. And it's very fast because there's only one way to the 19. And this is a finished picture of the tree. And so in that case, you go to the left, you got 0, call them 0, and you code 1 if they go to the right. So in this case, we will go to the left for character 1. Over here, we get to have 0, 0, 0, 0 for character 1. But the good thing for that, because we only probably gonna need to write his name in the script for once, and for character 19, we only have a code for 1. That's pretty easy because we have to write that 19 times, and we want that to be easy in the script. That's why we're using Huffman coding. And most importantly, the Huffman code makes sure every value you want to code doesn't have a children. So that's where the magic of no prefix. So you don't have someone have name of James Bond and someone have names James Carl, and when you're saying James, it could be either one of them. Just like if you're calling code number is 101 or code number 1, it can be any of these. And because over here is all start with 0, so you don't need to worry about the 19 person become any one of these. And